fact, Charles Abramson and I wrote a paper on kind of behaviorist approaches to studying novel creatures that you might use. Behaviorism is good for that because you don't have to make assumptions about what it is and what it's made of and how it got here. There's just a set of behavioral strategies that you use to test to see what this thing can do. Mm-hmm. So what we did was imagine we chose 3 of the nodes, chose 3 of the nodes. And just for an example, there were many experiments, but here's just one. Mm-hmm. You think of Pavlov's dog experiment, right? So in Pavlov's experiments, one of the things he did was you ring a bell, which is normally a neutral stimulus for a dog, doesn't mean too much. You present some food next to that stimulus. The dog salivates. You keep doing them together, and the dog will eventually associate the sound of the bell with the presence of the food, and eventually you just ring the bell and the dog salivates. Okay, that's the standard story. Is actually somewhat different, but that's the standard story of it. So what we did is we decided, okay, could we do this to the network? And so what we would do is we would stimulate one of the nodes. That means upregulate one of the genes. Do the same thing to another one where normally the first one has no effect on whatever the response we're looking for is. So we choose one of the nodes as we call it our response. Maybe it's something that controls blood pressure, or maybe it's something that is some kind of enzyme. It's something that we care about. And so we choose a node that always turns that on. We choose some other node that's the neutral node, that's like the bell, which normally has no effect on it. And we just present them together. We present them together, and then we pause, and then we present them together, and then we pause, and then we present them together. So when you do this, what you find out is that for certain networks and for certain choices of the conditioned stimulus node, the unconditioned stimulus node, and the response, it will actually learn to associate them so that later on, when you present just the neutral stimulus, it fires off the response. Now that's amazing. That means that this gene regulatory network has associative learning capacity. It can be conditioned like an animal can. Now, a couple of interesting things, the reason I bring this up, one is that random networks don't do this very much. Biological networks do this. So that means that evolution sort of selects for this, or directly or indirectly, but life likes this capacity. So that's one thing. But another thing is that choice of which of the nodes, so let's say you have a dozen nodes, so you can choose which of the nodes is going to be the conditioned stimulus, the unconditioned stimulus, and the response. That choice is not the only choice. You could pick 3 different nodes, or you could flip their roles around. And in fact, there's 6 different kinds of learning that it can do that have different, you can think about it as like a stencil, and you're sort of putting the stencil onto the network in different ways, and you're seeing different nodes in the roles that your stencil assigns. And so now you can do an experiment, and you can ask yourself, well, which of these different ways of looking at this network give me different capabilities? And so what you find is that for the exact same network, and so that's the key here, is that the learning capacity of this network was not due to changes in the weights, the traditional idea of like synaptic connections, right? The weights are changing. Nothing was changing. The hardware was never altered. It was exactly the same network. But depending on how I looked at it as an observer, I chose these 3 nodes, or I chose these 3 nodes, or these 3 nodes. Depending on how I look at it, I can squeeze completely different functionality out of it. I can get it to do associative conditioning. I could get it to do sensitization or habituation or different other things. In fact, simultaneously, some of these memories can coexist. And so this to me is a really powerful example, because what it means is that a single network, nothing was changed about that network, absolutely nothing. The hardware is exactly the same, and yet different observers can extract different utility from what it's doing. And of course, Josh's examples are also very powerful in non-living media. So this is the idea, right? Is that you change your perspective. You can improve what's going on by not to sound like some kind of a self-help kind of thing, but literally, right? In the system, the improvement comes from changing your perspective on things. Not by changing events. It comes from changing the way you look at those events. And so that leads to a view of evolution and biology in general as this multi-scale soup of agents interpreting each other and finding better and better ways to interpret each other and understand each other and extract utility from that. And then, of course, the better you understand some system, the better you get at hacking it. And hacking, I don't mean the negative thing where, you sort of abuse the system, although that certainly happens, right, with parasites and various other things. That absolutely happens. But it doesn't have to be negative. The reason we have a body instead of a bag of amoebas is that these cells are constantly hacking each other. They are constantly sending out signals that get each other to do various things that they otherwise wouldn't do. It's behavior shaping all, up and down the scale hierarchy. So that's the vision here, right? Is that it's just full of, it's a huge, microcosm of observers interpreting each other and finding new and better ways to decode and interpret what they're getting from their neighbors, from the level above, the level below, and so on.
One of the notes from, I think it's the first figure number 2 in the paper, it's the spatial causal emergence graphs that you have between determinism and degeneracy. I know this is getting very much in the weeds. I'd love to just touch on it before maybe going back out to discuss some more of the mechanical computing and the morphological computation as well. I think it's a little bit later in the paper. But for those spatial to causal emergences, sort of this micro macro dynamic that's happening there. And the figure looks very familiar to, similar to some of Eric Howell's work. I'm not sure if that was like brought in.
Well, Eric was a co-author on the first gene regulatory network paper. So if that's the figure the paper you're talking about, then he was a co-author on that. The
idea, if you could probably explain this better, but the way I understand it is that he has another paper called "When the Map is Better Than the Territory," the macro scale can actually give you more information than just adding up all the micro scales. Can you perhaps, and I know it's a very complex, that's a whole different divergence, but could you bring that into how it applies here? Because I wasn't quite able to I can sort of see the similarity or how it's related, but if you could expound on that, that'd be really helpful.
Sure. And I'm not going to do a better job than Eric would about talking about his own work, so you could have him on. But I think his work is foundationally important. It's incredibly important work. And what he basically developed was a way to quantify and make rigorous a debate that's been going on for probably thousands of years, which is, are there any higher levels like bodies, organisms, people, things like this, or should it really be reduced to talking about molecules and atoms and whatever else is underneath, right? I mean, people have been discussing that for a long time. And so he's found a way to quantify that, and his analysis shows that there are, and this is of course also the work of Giulio Tononi and other people like that, that with many others that have contributed to this since then, that basically have figured out that for certain kinds of systems, you actually gain more power. Power means better ways to control and predict the system, and you gain better predictive power by taking seriously these higher levels. And I'll give you just another simple example that I really like. There's this thing that many of your listeners will recognize. It's called the game of life. It's a cellular automaton. It's this big grid, right? The universe is this giant grid, and it has a very simple physics. It has each grid is a single node, and it can be either on or off. It's either bright or dark. And the way you determine whether it's on and off is you count up how many neighbors it has that are on. And then there's three simple rules that tell you whether that cell stays on or off. That's it. That's the physics. It's totally deterministic. There's nothing else in there. And so the magic that happens there is, and this is John Conway, I came up with this, is that if you run that world forward from certain starting configurations, you see all kinds of amazing complexity emerge. And one of the things that you see is this thing called a glider. The thing about a glider is it's a stable pattern that moves across the screen. Now, now let's keep in mind in that world, in life world, physics, there is no such thing as a glider. All that exists are individual, you can call them molecules or something that are just on or off, and they don't move, and that's it. There's no such thing as a glider. But to our visual system, we interpret a moving pattern of, just imagine a wave of these cells turning on and off and on and off, right? So if they do that in a pattern, you see this thing moving along. So our visual system is very good at turning those kinds of events into a mental representation of an object. It's not a real object in terms of physics. It's what you might call a persistent physiological kind of state, or like a hurricane or something else, that there are the molecules of air, yes, but then there's or a wave or an ocean wave. You got the water, but then you've also got this wave. Okay, so one thing you could do is you could be a strict kind of reductionist about that world, and you can say, look, there are no gliders. And I'll tell you why. You don't need to know about gliders in order to predict the next thing that's going to happen, because the world is totally deterministic. And if you tell me where all the on bits are at time t, I can tell you exactly what's going to happen into infinity. I just have to crank through the computation. I can tell you where everything's going to be. And this is true. However, what you don't have when you do this, if you don't believe in gliders, what you're not, yes, you can predict what happens after somebody else has set up a clever pattern for you. But what you're not going to do is invent a pattern in that environment that creates a Turing machine using gliders as a way to move bits around. Somebody did that. Somebody actually did that. They created it. I mean, it's incredible. Yeah. They created a computer inside of LifeWorld, and it uses these gliders to send signals around. That's the thing. It's not that the determinist, once you give them this amazing setup, it's not that they can't tell you what happens next. They can. They just would never have made one, because they don't believe in gliders. And so this once again gets you back. I know this is a little bit away from what you asked about Eric, but Eric's work. But I think it's important. It's the idea that, yeah, you can quantify prediction and control, and it's very awesome that his system gives you a way to say that in certain systems, knowing about these higher levels and looking at gliders as opposed to, and I actually don't know if anybody's done this exactly for the game of life, but this kind of thing, that knowing about these kind of higher levels, like, for example, in biology, you might say knowing about organs as opposed to just gene expression states, or knowing about persistent physiological states, maybe stress states, maybe waves, maybe calcium waves propagating through tissue, maybe electrical waves, whatever. Knowing about these things gives you extra power. But what we don't yet have a way of quantifying, and I think, I've been talking, I have a new postdoc coming that we've talked about doing this project next, is actually trying to come up with a quantification of the next step, which is not just prediction, but actually the inventiveness part, the generative part. Like, right, how much power does a certain lens give you to invent new stuff, as opposed to just say what pre-existing stuff is going to do next. I think it's really important going to the future. I mean, it's a super hard problem. I don't have a solution for it yet in my head, but I think it's really important, and we don't really have. But I think that's the evolution. That's the next evolution of the kind of thing that Eric did. If you want to dive deeply, specifically into morphological computation, Josh Bongard is the person I have on, because he was actually a very important. He did some very important work in this field, which, exactly as you pointed out, it talks about the kinds of computations that are done by the embodied cognition of the controller. So and there's some very interesting ideas in that field, like instead of for example, you might think, do I need to evolve a controller to control a certain body, or do I change the body to suit the controller? How do they relate to each other? Where is the actual intelligence? So there's many things, and so he could tell you all kinds of interesting stuff there. But for me, what I find interesting about it is this. Again, let's just back up and remember that what we're talking about when I say things like there's the organs in your body have intelligence. There's a trivial sense of it, and this is what people often react to when they object to these kind of statements, is they will say, well, look, you can just paint that onto anything. You can say anything is, here's a ball rolling down a hill, and you can say, look at that, isn't that amazing that it gets to where it's going? Boom, intelligent. So that isn't what I'm saying. What the TAME framework says is that that all intelligence claims are engineering protocols. That when you tell me that some particular system has a degree of intelligence, what you really need to tell me is, what's the problem space? What are the goals that the system can achieve in that problem space? And what degree of sophistication can I assume that the system is going to have on its own without me micromanaging it? Those are the three things that you are really telling me when you say, so